Uh, please go to post number 641 and fill in your details because I'm going to be using that to call names out during the lecture. So those of you on Zoom, again, it's post number 641. This is the attendance poll. Please fill it out. And again, shut your laptops, get your name tags out, folks, please. And we will begin. Okay, let me begin. Maukhik, what was the last topic we covered? Upsampling and downsampling in. Was that the last topic we covered?
There was something else.
So Katrina, what was the very last thing you were speaking about, just briefly?
Find the example, checking the example and put everything together.
We put everything together, right? And then we briefly mentioned training the network. So where we are now is we know how to compose a CNN. We know all the operations it performs. How do we train it? But just for completeness sake, let me do a quick recap. We're going to go do a quick recap, spend 10 minutes on this, and talk for the next class and a half about backpropagation through convolutional neural networks. So the story so far is that pattern classification tasks such as, does this picture contain a cat? Or does this recording include the word hello? Are best performed by scanning for the target pattern. Scanning an input with a network and combining the outcomes is equivalent to scanning with individual neurons hierarchically. We've seen that too. So the first level neurons scan the input, the higher level neurons scan the maps formed by the lower level neurons, and the final decision unit or layer makes the final decision. Deformations in the input can be handled by pooling. Now, for two-dimensional or higher dimensional scans, the structure is called a convolutional neural network. If it's a one-dimensional scan a long time, we call this a time delay neural network. Now, here's the general architecture. A convolutional neural network comprises convolutional and optional pooling layers. And the final layer, the numbers computed by the final layer are generally flattened and put through a multi-layer perceptron. So what does a convolutional layer comprise of? Now, a convolutional layer computes several output maps. Corresponding to each map is a filter. So within each map, there are two stages. First, we compute an affine map by convolution of a filter, representing a pattern of weights over the maps in the previous layer. And then once you compute the affine map represented by the Z, you apply an activation pointwise and compute an activation map as represented by the Y. Yeah. So how does this work? Computing the affine map. Here, of course, we saw how this worked. For every output affine map that you wanted to generate, you would have a filter. The filter would have as many channels or maps as the number of input channels. So again, the number of channels in the filter equals the number of input maps, right? And the number of filters equals, what does it equal? The number of output maps, right? And so the manner in which any specific output affine map was computed was as follows. We picked up the corresponding filter. We placed it at each position on the input collection of input maps and performed a pointwise product and a sum, which is effectively a dot product. You could add a bias if you're so inclined, and then you just scan the inputs and computed a value for every position. So that's how you ended up getting an output map. Now, once that the affine map Z was computed, then you had the pointwise application of the activations, which meant that for every filter, you had one affine map, and corresponding to every affine map, you had an activation map. Every input channel was or contributed to the computation of every output channel, every affine map. But then each affine map contributed to the computation of only one activation map. So each Z was computed from all of the preceding Ys, but then each subsequent Y was computed only from the corresponding Z, as the arrows in the figure show, right? So over here, the Z's, any given Z map actually uses all of the input maps. Any given Y map is only computed from the corresponding Z map. So, call 1. 5 seconds, guys. Pokemon Abra, what is the answer? Select is the number of channels equal to the number of input maps?
Yes.
Yes or no?
Yes.
Okay. Pokemon Arcanine, is the number of channels equal to the number of output maps, the number of channels in the filter?
No.
Okay. And Diglett, does the number of filters equal the number of input maps?
No.
And Shift tree, what about the fourth statement, true or false?
True.
Thank you. So we all got it, right? And okay. So that's how the convolutional layers are computed. The other set of type of computation here is pooling, where you have different kinds of pooling. Max pooling selects the largest from a pool of elements, where the pooling itself is performed by scanning the input with a max pooling filter. That's the terminology over here. So the size of the filter is the window over which you're picking the largest element, and it just scans the input. So at each position, you'll be sliding left to right, top to bottom. And at each position, you actually perform the max pooling in a two-stage process. First, you find the index of the largest value. And then second, you copy the largest value, the value at that index over. You could do this in just one step by just picking the largest value, but then that prevents you from performing backpropagation. So we need to know where the largest value came from, because this is how the derivatives of the max operation are computed. And then you read the value from there. And so that's how you perform max pooling. The alternative is mean pooling, where instead of picking the largest value in the window, you just compute the average value of the window and copy it over, and scan the input as before with a window. At each point, you replace the value that was there by the mean of the window. So here again, this is the pseudocode for the mean pooling. You're scanning left to right, top to bottom. At each position, you're pulling up a window of values from the input and computing its mean. Now, the pooling operation is performed channel-wise, unlike the convolution operation, where each output filter, the output channel was computed from all of the input channels. In the pooling operation, any output channel is computed only from the corresponding input channel. We also saw resampling. We can proportionately decrease or increase the size of the maps by dropping or inserting zeros. So downsampling reduces the size of the maps. If you want to downsample by a factor s, then after each column, you drop the next s minus 1 columns. After each row, you drop the next s minus 1 rows. Upsampling does the reverse. It increases the size of the input. So if you want to increase the map by a factor s, then after each column, you introduce s minus 1 columns of zeros. After each row, once again, you introduce s minus 1 rows of zeros. So this is the downsampling operation. You can think of it as a layer. There's a downsampling layer. I'm not sure where that music's from, but it's nice. And so you can literally think of it as erasing s minus 1 after s minus 1 rows after every row and every s row, and s minus 1 columns after every s column. So if you started with this image over here, if you wanted to downsample by a factor 2, you'd be erasing every second row and every second column and then compacting the whole thing together. It's a two-stage process. And the upsampling layer does the reverse. You just pull the thing out, and in the gaps, you just introduce zeros. So this is how you would upsample if you were upsampling by a factor 2. You just separate the whole thing out and introduce zeros. It's all very simple, right? And typically, downsampling is combined with the preceding operation. So if you have convolution followed by downsampling, you just perform convolution with a stride. If you have pooling followed by downsampling, you just make it pooling with a stride. So pooling is often combined with downsampling. Pooling is almost never performed without downsampling. Nonetheless, it's very useful to think of this when you're performing convolution with a stride or pooling with a stride. The fact that you have a stride makes direct computation of derivatives painful. If you've ever gone through blogs and textbooks and such like, they devote unnecessary amounts of space on how to deal with pooling with strides greater than 1 when you're convolving or pooling. The fact is, if you just separate these two operations out and always think of it as convolution followed by downsampling or pooling followed by downsampling, the process becomes trivial. Upsampling, again, is typically followed by convolution. Now, very often, for the same reason as before, you will find unnecessary amounts of text devoted to computing derivatives for fractional convolution layers, fractional stride convolutional layers, where you're essentially upsampling. If you think of it as an upsampling operation followed by convolution, an upsampling layer followed by convolution, the computation of derivatives becomes trivial. So typically, downsampling follows an operation. Upsampling precedes a convolution operation. Upsampling is almost never followed by a pooling operation. And we refer to it as convolution with a fractional stride. They're also called transpose convolutions for reasons that we won't get into here. So pooling with downsampling or convolution with downsampling, these are going to be resampling operations. Upsampling followed by convolution is also a resampling operation. And although these are implemented in practice as single operations, for our purposes, we will separate the two operations. Anytime you have a stride greater than 1, you're going to say it's the basic operation itself, followed by downsampling. And if you have a fractional stride, you're going to say it's an upsampling operation followed by the basic operation. So here's how we set up the entire operation end to end. If, for instance, you wanted to perform classification of an image of this kind, you'd separate out the R, the G, and the B layers. You'd pack them into a stack. And the CNN itself is a sequence of convolution and pooling operations. Now, corresponding to each of the convolution operations is going to be a set of filters. So if you stack things up like this, your filters are going to look like cubes because your filters are basically a collection of channels, right? We saw how this works. And so the number of how does the number of channels or maps in the output of this convolution relate to the number of filters? How does it relate to the filters? Pokemon, Caterpie. Okay, Pokemon Raticate. What's the how does the number of output channels relate to the number of filters? No. Okay. Pokemon Raichu. How does the number of output channels relate to the number of filters? There's no response in Zoom? Okay, what's it say?
The number of output channel is equal to the number of filter.
Thank you. Right? So we are going to have one filter for every output channel. And so similarly, now these channels are going to be compressed typically through a pooling operation because pooling is usually performed with a stride. And then once you get to this position, after you perform pooling, you would have another bunch of filters which are going to compute the next set of outputs, which would pool and so on. Now, there's one issue that not explicitly mentioned in the slides, but I'd like to mention over here, which is how do you decide how many channels you must output? Now, if I have this question for you. Somebody reply. If I have a collection of channels, so let's say this is n cross m, and there are k channels here. How many values do I have in all? N times nmk, right? So this is nmk. Now, if I perform some convolution or any operation, and then I want to retain all of this information, how many values must I have in the output? I must also have nmk values, correct? So if I'm convolving, so let's say I have k channels, and let's say I'm going to zero pad to retain all of my values. So just ignore edge effects. And if I'm convolving with a stride of 2, how many filters must I have to retain all the information? Pokemon Golem, how many must I have?
A plus 2.
What, pardon me?
Is it K plus 2?
K plus 2. Okay, somebody else. Pokemon Cluster.
2 times m times 2.
2 times
2.
This is going to be, if I take a stride of 2, this is going to become n over 2 m over 2, correct? So how many channels must I have? 4k, right? Otherwise you're going to lose information, correct? Makes sense to everybody? Right. Now, I may not perform convolution with stride 2. I may perform convolution with stride 1 so that the output remains n cross m. But then I follow this by pooling with stride 2. How many channels must I have? How many channels must I have? Pokemon Scissor?
2.
Yeah? Pardon me? Could you repeat the answer, please?
K plus 2.
K plus 2. Somebody was answering over here. Okay, tell me this. If I convolve with stride 1, the output remains more or less n times m. Then if I pool with stride 2, what will this become? Can you speak it up? Can you speak up, please? This is going to become n over 2 times m over 2. So how many channels must I have if I want to retain all the original information? 4K, right? So regardless of whether you are convolving with a stride or convolving normally, but then following up by pooling with a stride, if you do not want to lose information, then you want to increase the number of channels. So typically, and you want to increase the channels also to deal with the edge effects because you're going to be losing stuff. So typically what happens is that as you go through the network, you have sequential pooling operations. So the maps become smaller in size. So how do I compensate for that? I keep increasing the number of channels. Otherwise, I will lose information. Everybody with me? Right? So, okay. All right. And all the parameters that we must learn are going to be all the filters. Yes, Chetan. Thank you. That's a very nice question. If you do not want to lose information, you must increase the number of channels. In general, we want to reorder the information. We don't necessarily want to lose it all the way until we get to close to the classification layers. That's where you actually begin filtering out the garbage, right? And so we like to keep stuff. But you're right, there may be a lot of noise over the things that are unrelated to the primary task, which you would want to lose. So it's not always going to kill you to decrease the number of variables that you have remaining. But
just to start with all the information.
yes, right. Okay, and so these are all the parameters we would want to learn. All of the filter parameters must be learned, and the MLP parameters must be learned. Now, how do we train this network? As before, we're going to have a collection of training instances with the training instance and the class label. And for each instance, we can define the overall loss as the average divergence over the collection of training instances. And so we want to use backpropagation to compute derivatives. First, we want to use gradient descent, so we need derivatives. So you need the derivative of the loss, which means that you're going to need the average of the derivatives of the divergences for the individual training instances. You're going to need these guys, right? And that is what we must figure out how to compute, because once you have that, you have the rest of it. Now, here's what we have. I feed my input to the network. It goes through, some result pops out at the end. And now once I pop out a result over here, this final bit is just an MLP. So I can compute a divergence over here, compute the derivatives, and backpropagate it all the way back to the initial flat layer. But then how does this, what actually happens here? When I backpropagate, I'm going to compute two things. So I have all of these layers, and I have weights, right? I have the y, I have the divergence function, I have the desired output, and I compute the divergence. Now, I can compute the derivatives all the way back until I get the derivative derivatives with respect to all these w's. But then I can also compute the derivatives continuing backwards with respect to the input of this layer, because that's what backpropagation does, right? So at that point, you're going to have derivatives all the way until the input of the first layer of the MLP. Now, what is the input of the first layer of the MLP? The final convolution layer had a bunch of maps of this kind. And these were flattened into the first layer, into the inputs of the first layer of the MLP, right? So once I get the derivatives with respect to the first layer of the MLP, I can fold them back into the same shape as these maps. So these derivatives can now be folded back into the same shape as these maps. And that's where we're going to begin from. Everyone with me? Questions? Zoom? Any questions?
Okay.
And so, given that, now we're going to have derivatives with respect to the values of the final output maps, and the final convolution of pooling layer, right? And those derivatives must now be propagated backwards. So where are we? As far as we are concerned, we have output derivatives with respect to all the y's in the final layer, which are the activation maps, and we must sort of back propagate them through the convolution layers and through the pooling layers. So for the convolution layer, there are two things. In a convolution layer, you have the final activation map. This was computed from the affine maps, which were computed from the input maps. I'm using the term maps because they look like maps. If I use the word channel, maybe it's not so apparent what I'm talking about. These are effectively maps of the original input, right? And the computation of these affine maps from these convolution layers was performed using these filters, right? So when I compute the derivatives, I have derivatives with respect to these y's because this is what I got when I folded things back, right? And so from the derivatives with respect to these y's, I must compute the derivatives with respect to these z's, go back and compute the derivatives with respect to the previous y's, and also the derivatives with respect to the filters. Similarly, in the pooling layer, I would now have the derivative with respect to the output of the pooling. I must take it back and compute the derivatives with respect to the input to the pooling. And so overall, here are the things we've got to figure out. The assumption is that we already have the derivatives with respect to the, that having gone through at any point, we already have the derivatives with respect to the output maps of the layer. And we must now back propagate those derivatives back to the input and any other intervening parameters. So for convolution layers, we have to figure out how to compute the derivatives with respect to the affine values z, given the derivative with respect to the activation values y. And then given the derivatives with respect to z, we must figure out how to compute the derivatives for the filters and the previous channel. For the pooling layers, given the output of the derivatives with respect to the output of the pooling, we must figure out how to compute the derivative with respect to the input to the pooling, right? So let's look at this guy first. I'm given the derivative. You have performed your convolutions with filters. You have your affine maps. Now those affine maps have been used to compute activation values. So you now have derivatives with respect to the activation values. How do I compute the derivatives with respect to the affine term, right? But then that's easy. So I'm assuming over here what happened. I'm assuming over here that we have, these are the z's, these are the y's, and each point over here computed the corresponding y, right? So we have, I'm leaving subscripts and superscripts out. I'm saying yij equals some activation function of zij, and I have the derivative of the divergence with respect to d yij. So what is the derivative of the divergence with respect to z? Pokemon Nidoqueen. What is the derivative? Okay, Pokemon Ariados. what is the derivative with respect? It's okay to say, I don't know, right? But what is the derivative with respect to z, given the derivative of the divergence with respect to y? Pokemon Ariados? No? Okay. Pokemon Corsola.
df
What is
dz.
Pardon me?
I mean f prime z might be the
Thank
answer.
you, right? Thank you. So there's going to be d dive over dyij times f prime z I comma j, right? Everyone with me so far? We haven't done anything magical. Okay? So this means we now know how to compute the derivatives with respect to the affine maps given the derivatives with respect to the activation maps. So this is done. The first one, we know how to compute derivatives. Oh, go back. What is happening here? So we now know how to compute derivatives with respect to these guys, right? How to compute the derivatives for z's given derivatives for y's. Now let's see how you can compute the derivatives for the filters and the previous y's given z's, the derivatives for the z's, okay? This ends up being a little involved. And so we can just look at the math. Again, in the forward computation, we have computed all the affine values, all the z's, right? And all the y's. We have w's. Now back propagation, given the derivative with respect to the z's, we want the derivatives with respect to the y's and w's. So basically, there are two different terms that we have to consider. The input maps y convolve with the filters w to give you the output affine maps z. So if I have the derivatives with respect to z, I have to figure out what the derivatives are with respect to the input maps y and what the derivatives are with respect to the filters, right? There are two different derivative operations to be performed. So let's just consider the first one. So do you see how we are breaking this up step by step, right? So here's where we are. I already have my derivatives with respect to the z's. What am I computing the derivatives for? The y's, all the way back there, okay? So let's see how to do this. Let's see how the influences are computed. All of the input y's influence every single output z through the filters, right? So every input channel works through the corresponding channel of the filter in computing a given output channel. So extending this, every input channel influences every, I just do a simplified picture. So the edge shows you which filter. So the filters have, I'm showing you a subscript and a superscript and terms in parentheses. So the subscript basically tells you the input channel number. Right? The subscript's the layer, yeah. The subscript's the layer, and the terms inside represent input and output channels. But you don't really need to look at the symbols over here. It's pictorially fairly clear, okay? So every input channel influences every z. In fact, every input channel influences, the entire set of influences is shown by this picture. But then, if I'm interested in computing the derivatives for any given y, how many output channels does it influence? So any given y influences how many output channels? Pokemon Fiero. Okay. Pokemon Houndour, that's Jackie Wo. How many output channels does any given input channel influence? All of them, right? So this is what we've got. If I look at this one, this is the complete set of influences. And so now if I want to compute the derivative for the y, that's one channel of the y, how many terms does that sum over? How many terms must I sum over? Basically, all of the output channels, right? Thank you. So, if I want to write the math, oh, come on. So, if I want to write the math, this is what it's going to look like. The derivative with respect to any particular channel of the input is going to sum over all of the output channels, and and within each summation term is the product of the derivative of the divergence with respect to that z times the derivative of the z with respect to the y. Right? Simple distributed chain rule. And this is the term that we need to compute because the derivative of the divergence with respect to z is already known. So now these derivatives, you're going to have one derivative for every single output channel, right? Every one of these can be differentiated with respect to the y. So let's consider any single one. The derivative of the nth affine map with respect to the elements of the nth affine map with respect to the elements of the mth input map, okay? So again, we want to compute the derivatives of the elements of the output map with respect to the derivatives of the input map, or more explicitly, specifically, we aren't even interested in individual derivatives. We are interested in the derivative of elements of the input map with respect to the output map, right? So now consider this one element highlighted in red. That is the 1, 1 input value, right? So when I place the filter, this is the same picture that we saw in the last class. If I place the filter on top of this map, which output value am I computing right now? The 0, 0. So clearly this element influences the 0, 0 output value. Does it influence the 0, 1 output value? Because if I slide the filter forward, I'm going to be using this also to compute. If I slide the filter forward, it's going to be influencing the computation of the first element, right? If I slide the element 2 steps forward, then it's out. Similarly, when I slide the filter downward by 1 position, it's going to be using 1, 1 to compute this term, and this guy here, this term. And if I slide the filter 1 down and 1 right, it computes the 4. But then if I slide the filter any beyond that, the element is the highlighted element is not going to be involved in the computation, right? So when I want to compute the derivative of the divergence with respect to this guy, I must sum over these 4 elements, right? So, but that's just one channel. That element is going to be influencing the same 4 components of every output channel. You guys with me? And so, if I want to compute the derivative of the divergence with respect to this element, I'm going to have to sum over all of these maps. That's a sum over n. And within each map, I'm going to have to sum over all the elements that it contributes to. And the term I will sum is the derivative of the divergence with respect to each element times the derivative of that element with respect to this guy. Everyone with me? Questions? So this looks complicated, but is it?
Question.
Yeah.
What if the stride is not 1?
Pardon me?
What if the stride is not 1?
So we are always going to assume that the stride is 1, because if the stride is not 1, you will separate it to to a sequence of 2 operations. The first one is a convolution with stride 1 followed by a downsampling. So we will deal with the derivatives of downsampling separately. As far as the convolution is concerned, you must always, always, always assume that the stride is 1, because a stride greater than 1 can be peeled off as a downsampling layer. That answer your question?
Okay. Yes, thank you.
Okay. So how does a single element in the input influence the various values in a specific output map? I'm using, now remember, any particular input channel is going to work through the corresponding channel of the filter, right? So this is going to be the mth channel of the nth filter, which determines how the mth input channel contributes to the nth output map, right? So the filter, I'm showing the filter, representing the filter using 2 different mechanisms. One is through colors. The other is through indices. We will be using both for the illustration. So in this case, the filter is a 3x3 filter. It has 9 elements, all indexed, 0, 0 through 2, 2. And then every element of the filter also has a color, as you can see. Now we're going to be placing this filter at the top left corner at the 0, 0 position. To compute, what would you be computing when you place the filter there? The 0, 0 of z, right? And y22 contributes. So here it is, right? What is the contribution of y22 to z00? So z00 is going to be the filter 22, w22, times y22 is going to be contributing to z00, as you can see, right? So here's the equation. I'm going to say z00 plus equals, because obviously there are other terms contributing, y22 times w22, right? Now, let me slide that forward. How does y22 contribute to z10? Anyone? Pokemon Ludicolo? How does y22 contribute to z10? This is Hitmonchan, Pokemon. How does y22 contribute to z10?
It
Yeah.
gets multiplied and added.
Pardon me? Could you repeat that, please?
It gets multiplied with W.
Which W?
1, 2.
Exactly, right? So y22, the pink color gives away the answer, right? y22 multiplies z12 to give you, the w22 multiplies y12 to give you z01. And how does, how does y22 contribute to z20? Anybody? So y22 multiplies w02, as indicated by the colors, right? Now if I go down 1, then why does this skip 2 steps every time? Okay. How does it contribute to z01? Anyone?
1.
Multiplies 1, right? And so that's how the computation goes on. Does anybody see a pattern? Does anybody see a pattern in the indices?
It's another convolution type thing.
Here is the thing. The index of z and w sum up to the index of y every single time, right? It's 2, 1 plus 0, 1 is 2, 2. 1, 1 plus 1, 1 is 2, 2. 2, 0 plus 0, 2 is 2, 2. So the index of the output and the index of the filter sum up to the index of y. Do you see that? Right? Every single time. And so you can see this visually. You can just follow this, right? So in general, for any position x prime, y prime of the output, the contribution of xy is going to be which element of the filter? So again, what was the pattern? What did we observe? Sunflora, what was the pattern we observed? Pokemon Sunflora. Okay, Pokemon Vaporeon. What was the pattern we observed? Okay, Pokemon Umbreon. What was the pattern we observed? Okay, Pokemon War Turtle. What was the pattern we observed?
We observe that x prime plus the filter index would give you the input index x.
XY, correct? So what would the
Yeah.
filter indices be?
X minus x prime, y minus y prime.
X minus x prime and y minus y prime. So you see how this worked, right? I could write the equation down. It wasn't particularly complicated. You just had to observe the patterns. Everyone with me? Okay. And so when I say the derivative of z x prime y prime with respect to y x y, what is it? What's it going to be? Just using the formula. Guys? Which is which index? X minus the difference between the two, right? The derivative of z x prime y prime with respect to y x y is going to be weight x minus x prime y minus y prime. Straightforward, right? And so given this, now I can go back to this formula where when I'm computing the derivative of for any xy element, I have to just sum over all the maps, and then over all the maps I've got to go over all of the elements. The elements that it doesn't influence, you're going to get a derivative of 0, right? And so, and over all of the elements, I multiply the product of the divergence with respect to that particular output element times the derivative of that element with respect to y. And this guy here, what is d's derivative of z x prime y prime with respect to dy xy? That's just going to be weight x minus x prime y minus y prime. So you can just plug this formula in, right? And this looks complicated, doesn't it? So, yeah. All right. First question, Pokemon Chansey. What's the answer?
True.
True, thank you. And Hoot Hoot, what's the answer to the second one? Pokemon Hoot Hoot? Yeah, that's you? Okay, sorry. All right. Pay attention, guys. What is the answer to the second one?
True.
Also true, everybody agree? Right? So, come on. Okay, both of them are true, right? This looks like a complicated operation over here. But the fact of the matter is just a convolution. It's a very trivial convolution. How so? This is the formula we just saw. And to see how this is a convolution, I'm going to go back and see these colored pictures, okay? Now here again, that's the filter. It has two separate indices, as you can see. And it's going to be convolving the y map to give you the output z map, right? Now look at how, when I position the filter on top of the y map, which element contributes to z0, 0? That's the 2, 2 element, colored red, right? The element, so the derivative over here that I'd be multiplying, the derivative for z0, 0 is going to be multiplying w22, correct? So this guy, the 1, 2 element shown in pink is what is going to be multiplying the derivative at z1, 0. Everybody see that, right? And the 0, 2 element, or is it? No. yeah, the green one, the 0 to element is going to be multiplying the derivative for z to 0, as shown by the color, right? And similarly, again, I'm still computing the derivative for y22, but then the derivative for z01 is multiplied by the light green weight, which is w21, right? And so on. What do we see? Do you see a pattern? Upside down, upside down, and left to right. All I did was flip my filter top to bottom, left to right. And where did I position it? I positioned it so that the 0, 0 element of the filter sat on the 2, 2 element of the output. Do you see that? Right? And then I just multiplied the elements of the filter with the derivatives for the underlying, the z underneath, and then sum them up. So I flipped the filter up to upside down, left to right, okay? And then I positioned it so that the pink element, the 0, 0 element of the filter, sat on the 2, 2 element of my output to compute the derivative for y22, right? If I wanted to compute the derivative for yxy, how would it sit? Just extending the logic, how would it sit? How would xy, right? The 0, 0 element of the filter is going to sit on the after reflection. It's going to be at the bottom right, and it's going to sit on the xy position. And so here's what, this is what, so if I looked at the derivatives, right? I had the derivative map over there on the right. To compute the derivative for y22, I flipped the filter left, right, top to bottom, and put the bottom right corner of the flipped filter, which corresponds to the 0, 0 index of the filter, on 2, 2, and then just performed an element-wise product of the filter with the underlying derivative values, and then sum them up. Or more generally, if I want to compute the derivative at any xy, I'm just going to flip the filter left, right, top, bottom, and place it with the bottom right corner at xy and perform a component-wise product and multiplication, which is just, what is that operation? It's a dot product, right, at this point. And of course, this is from a single map, right? Now, here's something else. I have my derivative with respect to z. I want the derivative with respect to y. Say I'm not zero padding, right? How many elements how many derivatives do I need to compute? Over here, in this example. The size of y, right? But how many values do I have on the output? The size of z. But then we know that the bottom right corner of this reflected filter has to sit at the same index that of z for as the index of y for which you want to compute the derivative, right? Clearly there's no room over here. How would you deal with it? Pad it. Thank you, right? So I'm going to flip my filter top to right and bottom, left to right. I pad my output map with zeros, right? Place the filter like so in a product, right? And then I can just slide forward, and I'm computing derivatives for every element. Where will I run out of elements? And how many elements am I going to compute? Exactly the size of y, right? So how many rows and how many columns will I be padding it with? Filter size minus 1 on every side. Does that make sense visually to all of you guys? Right? Very simple, right? The math looks a lot more complicated than the actual operation when you draw these things out and visualize it. But the thing is, so that's the derivative at, general formula for the derivative. But then the derivative at any location is derived through all the output maps, not just one output map. Correct? So what must we do? So let's say I want to compute the derivative of the mth input map. I'm going to pick up the mth channel of all the filters. Right, now observe that I'm picking a row from the sets of filters. I'm not picking the mth filter, I'm picking the mth channel from all the filters. Okay, so I took a row and made it a column effectively. So that's like a transposition, right? So those are the mth channels of all of the filters. And then I flipped all the those filter channels, left, right, top, bottom. And then I padded the input derivative maps 0 all around. Place these reflected and flipped filters. Now we're going to have as many of these guys as the number of output channels, right? Because you're picking the mth channel of all filters, which is going to give you as many of these guys as the number of filters, which is the same as the number of output channels. And then just perform your computation like so, right? Just your standard convolution. After this, mirroring. Yes, Chetan.
Verify by picking the nth row from all the filters, we get the same number of outputs. Then we flip that channel map, and because the derivative there is just the weight, we just go across the output.
The output derivatives, basically. Yeah, that's exactly it, right? And the reason you pick the mth channel is because the mth channel of all the filters is what convolves the mth channel of the input, right? So beautiful. That's the entire derivative operation. Once you look at it, it's so simple. The math looks a lot more scary. Yes?
Just to clarify, so for every element, then you add up the derivatives of all of the.
This is just a convolution operation, right? I flipped the, let me show this. I flipped the filters. What happened here? Come on, yeah. I flipped the filters, 0 padded, it's an inner product. So the filter value times the underlying derivative value. You do it over all the colored elements here and sum them up. Questions? Yes, Chetan.
That last column that you have there, you're multiplying the weight times the derivative that we already computed.
Yes.
Just back to the output.
Yes.
I still quite don't see where are we taking the row here? Isn't this like the same operation?
Yes, but this is so. Wait a minute. I have too many. There's a little too much animation here for. We pick the mth row of all the filters. Okay, and then this is just the mth row of all of the filters, like laid top to bottom. So that's like a transposition of the filters. Then you're picking the nth value because you're going backwards.
Right.
Going backwards is always a transposition of going forwards.
So we're just multiplying the flip filter with the derivative value already computed.
Yeah.
And we're doing that for all of the filters and then just summing it up.
Yeah, that's it. Right. So again, once you look at the pictures make it obvious what is going on. The math often doesn't, right? Yes.
Question as well. This YL-1 is before Boolean operation or?
Whatever the input to the convolution is. It doesn't matter what it is, the input to the convolution, whatever it may be.
With, without.
It doesn't matter. It's the input to the convolution operation, right? Is there any other question? No? Okay. Yeah. All right. And so you find that, now observe that I added 2 times k minus 1 zeros, right? And I'm convolving it with a k size filter. So it's going to lose k minus 1 zeros. That gives me an extra k minus 1 elements. But then I lost k minus 1 elements going forward, and this is compensating for it. Right? When you went forward, if your filter size was k, you lost k minus 1 rows. So you have to compensate for it. So you're padding 2 times k minus 1 rows, but then you're convolving with a k size filter, so you lose k minus 1 elements. So you're going to lose one of the 2, and you end up with a derivative which is the same size as the input itself. And so now, if you actually perform 0 padding going forward, then the derivative is going to be the same as the size of the 0 padded input, and then you're going to have to peel off this 0 padding derivatives of the 0 paddings when you go back further, right? As we mentioned earlier, we may zero pad stuff to make sure that the sizes are fine, right? 10 seconds. All right. Pokemon Celebi, do you want to tell me that first statement is true?
Yeah, it's true.
Thank you. And Pokemon Arbok, the second one?
False.
False? Is that false or true? It's
Oh,
true.
sorry.
It must be. Okay. All right. And Pokemon Mary, what about the third one? And Pokemon Onyx? Pokemon
True.
True. Okay. Thank you. Okay, the last one. The output of the convolution doesn't need to be flipped back. That was wrong, right? You just get the correct answer in the correct shape. So, but the rest is not true. So here's the overall algorithm for computing the derivative with respect to the input to the convolution. Okay. So I'm going to skip the pseudocode. The one thing that remains is the derivative with respect to the weights. Now I can use the same logic. So let's say I'm computing the derivative. This animation is horrible because MATLAB keeps changing the color map. I was just trying to show you how every weight influences every output. And just focus on the little blue dot in the center of the filter, just for illustration. Observe how it influences the computation of every single output, right? So every filter element is going to influence every single output, but a filter element is going to influence the output of only one output channel, not all output channels, unlike the Y's, right? Because a single filter produces a single output channel. And so if I want to compute the derivative of, say, the filters, divergence with respect to the filters, each filter element affects several values within a single output map. So to see how this works, let's consider this one element, which is the well, in this case it's the one-tooth element, right? One-tooth element of the filter. And how does it influence the Z00? Now what was the rule we had earlier for the indices? Anybody remember? What was the rule we had?
The sum of Z plus W is equal to.
The sum of the indices of Z and W equal the index of Y, correct? And so if you have 0, 0 plus 1, 2 gives you 1, 2, right? 1, 0 plus 1, 2. I'm keeping the index of the filter fixed because I'm interested in computing the derivative of the divergence with respect to the filter index, right? And in every case, you see that it's used in the computation of all the Z's, but here is what we got. We got for any given Zxy, right? The index of Z plus the index of W gave me the index of Y, correct? So Zxy equals plus, right? There should be a plus. I just missed the plus. W12 times Y of X plus 1, Y plus 2. Or generalizing, for any xy position in Z, the contribution of the ijth element of W is through Y of X plus Y, Y plus J. We're still using the same logic as before, right? And so now, if I want to compute the derivative of Z, I already have the derivatives of the divergence with respect to the z's. I just need the derivative of z with respect to w, right? And so based on this, what is the derivative of zxy with respect to wij? Y x plus I, y plus j. Everyone with me? Right? And so, easy. So all I have to do, again, unlike the case of the input maps where I had to sum over all of the output channels, I just need to consider one output channel, but I need to consider all the elements of the output channel. And so the derivative of the divergence with respect to any ijth element of the filter, the nth filter, the mth channel of the nth filter, right? The mn. The indices can get confusing. Let's not look. You can sort of figure these out. I'm more interested in the ij's. The derivative of the divergence with respect to any wij is the sum over all elements of the output map over here, which is going to be the n, because it's very specific to the filter. And it's the sum of the derivative of the divergence with respect to the z element times the derivative of the z element with respect to the filter. And what is the derivative of the z element with respect to the filter? What is the derivative of the z element with the zxy with respect to wij?
Just y x plus I.
This guy, this is already computed. This term is y of x plus I n plus j. I can just plug it in here, right? This is an easy formula. We can implement it. But what I'm going to say something more. What do you think I'm going to say? What kind of an operation do you think this is?
Another convolution.
Another convolution, right? So, yeah. This is just, I'll actually just go straight to this, right? So we know where the formula came from, but this is just a convolution. And to see how this is a convolution, let's look at what happens here. So forward operation, each filter produces an affine map. Now let's go back and look at this, right? If I want the derivative of W12, Zi, the Z had to be positioned at a specific element, right? Because specific position. And where was it? Where was it? The derivative of Z had to be positioned at a specific position. Where was that? Every Z, so every Z index was multiplied by the W index to get the corresponding Y position, right? So which means that the entire Z map had to be positioned at Y12. If I wanted to compute the derivative for W00, then the entire Z index had to be positioned at Y00, because I start at Y12 and then I keep summing over the Z indices, correct? And so this is basically what happens. So let's say I want to compute, let's consider the second map of the first filter, second channel of the first filter. So that connects the second input channel to the first output channel, right? And now I already have the derivatives, so that's all I need to focus on. The rest can be ignored. The rest don't matter. If I'm trying to compute the derivative of the second channel of the first filter, the rest of the terms can be ignored, right? These are the only things that matter. And so I already have the derivative of the divergence with respect to the output map. To compute this term, the derivative with respect to the filter, I'm just going to be placing that output derivative map at the 0, element of the input map, not the derivative of the input map, but of the input map Y itself, right? And then just performing a component-wise multiply and a sum. And that gave me the derivative for W00. And then I can slide that forward 1, place it at 0, 1, and perform a component-wise multiply and a sum. That's going to give me the derivative for W01, right? And you can see how this goes. This is how the derivative goes. So very simple, right? This is a convolution, and it's the most trivial convolution you can think of. There's no flipping even. And so if I have the derivatives for any particular output map, output channel, and I want to compute the derivatives for all the channels of the filter that composed it, then I'm just going to place this guy. I'm going to convolve this guy with this one to give me the first filter channel, this guy with this one to give me the second filter channel, and so on. There is no zero padding, the sizes will match up, yes.
So you convolve with all of the output maps to get like
You compute the no, this is for an entire filter, right? So the filter has as many channels as the input map. So you convolve the derivative of the output map with the input channel to get the corresponding channel of the filter. Right? Questions? Anyone?
Yes, because each filter is
Exactly. Right. And then questions? Anybody? Yeah.
So for each output filter that we're getting from calculating the dot product, does that correspond to a bunch of weights, or is it just one particular weight? Like, I didn't quite understand what W of 1 comma n is in this slide. I guess that's the question.
So W of 1 comma n is the first channel of the nth filter.
So
that's it.
Is that the weight that's corresponding to the first channel of the input, the first input, and then the nth
output channel? Yeah, nth filter.
Okay, so that just, for every filter and every input, we get a corresponding output.
Right? So everything should match up. Right? Oh, you didn't see that. Especially the Pokemon that I'm going to call out. Marowak, you haven't seen that. I know. You haven't seen that with our previous slide. Five seconds. Thank you, Vibha. What's the answer? First one. You saw it. The first one's true, right? The derivative for the mth channel of the nth filter is computed by convolving the mth input channel by the derivative map for the nth output channel, right? I mean, it's kind of written in a very convoluted way, but you get the idea. So I have some pseudocode, but I'll skip it, right? It turns out that if you look at it through code, through the lens of code, it's even more simple than the operations that I just explained. But the convolution operation looks scary. The derivatives look scary till you actually begin drawing pictures and painting them, and then you realize there's nothing going on, right? It's very simple. Okay. But anyway, so we've taken care of the convolution. The next thing is, so the convolution layers are dealt with, right? For pooling layers, we've got to compute the derivatives for pooling layers. How to compute the derivative of the input of the pooling layer? Yes.
I just found out when we are trying to, just so when we're calculating the weight, so the derivative of the z by the weight, that's a convolution?
No, the derivative of the divergence with respect to the weight. It's a convolution of the derivative of the divergence with respect to z and the input.
Yeah, so what about the derivative of the divergence with respect to the inputs?
That we've already done, right? You took the filters and flipped.
Is that also a convolution?
That's what we've spent a lot of time explaining, didn't we?
Okay, so
where you just took you flipped the filters and then convolved, right?
Okay, so for this, for calculating derivative with respect to the weights, we don't need to flip it, but
that's right.
With respect to the
Yeah. Okay.
So is that being like convolved over like all the W values?
Yeah.
For the first.
It's exactly as we saw in the figure, right? For the inputs, you're going to be picking the corresponding channels of the filters, then flipping them and convolving. Okay. So now let's go over the pooling layers. I may run out of time, but I'll pick this up in the next class. We have a little time. So pooling, as we saw, groups a bunch of values, right? So let's try to do this with a figure. I won't actually do the math over here. And you guys answer my questions. So this is Pokemon Haunter, right? Suppose I'm pooling here, and I have looked at these 4 elements, and I picked this element as my output. So this is my input. I'll call this yi. This is my output yo. And I have the derivative of the divergence with respect to yo. Which of the input elements will the output derivative contribute to? The shader. So no, but this was for Pokemon Haunter, right? You there? Nope. Pokemon Seattle, that's you. Okay, you already answered. So because if I have y equals yo equals max of a bunch of elements, then only the element that's actually selected affects the output. Perturbing these guys does not affect the output, right? And so whatever derivative I have over here, this is simply going to get copied here. What values will these pick up? 0, because they do not affect the output, right? But then I slide forward by 1. And I slide forward by 1. And let's say even for this window, the same element gets picked up. Then what happens? You would add it up, right? This term is going to get added here. And these guys, they're just going to get zeros, additional more zeros. That makes sense to everybody? Right? Now you see why you need to retain the index of the maximum element going forward. You know which one inherits the derivative, right? And so you're going to max pooling is just going to be picking up the index of the max element, and then you're reading the value there. When you're computing the derivative, you're just going to be copying the derivative at the output map location that it contributed to into the location of the max, right? And if you actually want to do this correctly, you're going to be doing this is the forward operation. And the reverse operation, you'd be doing a plus equals, simply because if the same element contributes to the outputs at multiple locations, all of those derivatives must be summed, right? So again, mean, same thing. Suppose I have a mean. Now let's go back and consider the same thing. I may run over by a minute. Just bear with me, folks. So suppose I'm looking at this guy, and I computed the mean value and filled it here, right? So this mean is y11 plus y12 plus y21 plus y22 over 4, right? I got some derivative here. How does that contribute to the derivatives here? Divide by 4 and just distribute it uniformly over all of the elements that contributed to it, right? And so you get the divergence, derivative of the divergence with respect to the output element, just distributed uniformly. And then again, as before, as you slide, if the same element is being used in multiple windows, what happens? Just add them up. So basically, this is a convolution. What does this look like? It's the convolution of the output map with a filter which is all ones, all 1/4s, right? So, easy. And so we've seen how we can compute the derivatives for all of the most complicated operations, pooling and convolution. What we have yet to do is to figure out what to do if you have a stride greater than 1 or less than 1, right? But for now, We've seen that a convolutional neural network is a supervised version of a computational model of mammalian vision. It includes convolutional layers comprising learned filters that scan the outputs of the previous layer, and pooling layers that operate over groups of outputs from the convolution layer too. And typically, they're used to reduce output size, not network size. I'm sorry, that should be output size. Take note. Error. Okay. The parameters of the network can be learned through regular backpropagation. Max pooling layers must propagate derivatives only over the maximum element in each pool, and derivatives must sum. And the key piece that we also learned in the whole process is that regardless of the kind of operation you perform, if you have, if you have any operation which takes in some m elements in some shape, right? And it doesn't matter what the shape is, and produces some output in whatever other shape, and all of this is being used to compute the divergence. When you come back all the way here, how many elements must the gradient have, and what will the shape be? I'm speaking of the gradient. It's going to have the same number of elements as the input in the same shape as the input, right? Regardless of whether you're downsampling, upsampling, squeezing, compressing, whatever, nonlinear operation, doesn't matter. When you come back, all of those operations are going to get undone, so you end up with derivatives, gradients, derivatives are transposed, right, of the same size and shape as the input. Okay. I'll stop here. Any questions? No? Thank you very much.